Okay, so go through part 2, of which we already we went through part 1, so now we'll go through part 2. All right. So thermodynamics equations, exam questions. So this is the first question. Says, so these are just exam practice questions. So for the reaction, all right, for the reaction, we have hydrogen there 2, fluoride 2, then giving us hydrogen plus fluoride 2. So it's a dissociation reaction, and we have been given internal energy as negative 114.2 okay, calories per mole at 25 degrees Celsius. Calculate delta H. So delta H they're asking about is enthalpy. So what you do for you to actually master this question, this type of question, so what you do is we need to know that change in enthalpy, all right, just a bit, change in enthalpy, all right, will be given as number of moles. If at all we have number of moles, then Cp, all right, delta T, or just the T1 T2 minus T1. So that's how it will be given, right? Then again we have, so you need to judge, these are the equation you find, all right. So let me do this, or just let me write you. So internal energy, all right, will be given as N number of moles, then Cv, then D dt, which is change in temperature. So you need to know this equation again, since from first law of thermodynamics we know that internal energy will be given as, all right, internal energy will be given as um will be given as Q, all right, minus W, all right. So under first law again, enthalpy will be given as the same energy, all right, the same energy, then plus work. Okay, so we need to actually master these equations, all right. So and this work, sometimes it we know work is PV, all right, and from a first ideal gas equation, or just ideal gas equation, we know that PV is equal to nRT. So it depends on what, on the data that you have been given. For this case, we have the data of this and also the data of moles here. So temperature also have been given. R, which is the gas constant, is not the problem. So I'll go with this one. So they're asking me this one. So they're asking me enthalpy. So I'll get this equation. So I'll say change in enthalpy is given as change in internal energy, then plus work. So this work I'm given is, now it will be just the PV, of which it is nRT. So I'll say change in enthalpy is given as change in internal energy, all right, then plus nRT, like that. So where there is change in mole for this case. So what I'm going to do, I've been given internal energy, of which it is negative 14.2 kilo, all right, kilocalories per mole, all right. Then I'll say my plus, let me find it first, the same work, nRT, all right, nRT will be given as nRT will be given as, we can just substitute, I'm just substituting this, so the number of moles, so there was change in number of moles. So what I'm going to do is, I'll say the number of moles will be given as, the change in moles will be given as product moles minus reactant moles, of which I have product moles, I can see there's one there and also there's one here under fluoride. So that will be 2 minus, there I only have 1 there. So I'll say 1. So the number of moles is 1 mole. Okay, so substituting in the formula, so we are saying that is 1 mole times the gas constant that I'll use, since I have calories here, so I'll use the same calories for R. So I can say you can use 2 calories or just 1.987. So I'll write 1.987. Okay, Then from there I'll say I'll multiply now times the temperature. So temperature, we have 25, okay, 25 plus 273. So this will give us what? 298. All right, so that is it. So I'm saying now I'll multiply with the temperature there, which is 2, by the way, 298, like that. So punching that, okay, so this will give me 0 point, 0 point. All right, it's supposed to give me 0 point. Yes, it is 0.59, like that. Okay, because what I would do first, before 0.9, what I would do is I want to take it even in kilos. Okay, so I'll divide throughout by what? By 1000. Okay, so you can punch divide by 1000 so that it can fit the kilo, just like the friend here. We have kilo, so that will give me 0.592. Okay, so I'll just bring this 0.592. Then this will give me what? When you add this, they will give you, let me just punch, then that will give me negative 13.6. It is in kilo, by the way. Then we have calories. You follow the units, so it is per mole. They were in 1 mole, so this is per mole. Okay, just the calories will tell you the units. Okay, so this is what you are supposed to do. Okay, let's go to the next question. So calculate the value of change in internal energy. All right, then also change in enthalpy on heating 64 grams of oxygen from 0 degrees Celsius to 100 degrees Celsius. So what we need to know is that same under CV, all right, we know to say will be given as change in moles. By the way, I need to write to say this formula, the one they have been given. Change in internal energy will be given as change in number of moles, right? Then CV, all right, then change in temperature, like that. Okay, which is just delta T. Again, enthalpy, I'm from talking about this, you say it will be given as change in number of moles, CP, then change in temperature. All right, so what we need to know is that these are what we call Kirchhoff's equations. They are what we call Kirchhoff's equation. All right, so just a matter of substituting. We have been given CP and CV. So what we don't have here is the number of moles. We have the temperature change. So calculating the number of moles of oxygen. So say number of moles of oxygen given the mass, all right, 0.0. Then divide by the what? The molar mass. The molar mass of oxygen is 16. So when divide that, that will give you 4, right? So we have 4 moles. So it's just a matter of sub. So calculating this now, calculating. I'll start with the change in internal energy, which will be given as the change in moles. It is 4. All right, 4 moles. In fact, let me not even input the units. Okay, then times the CV that we have here is 5. So that is 5. Okay, so 5 again times what is the change in temperature. So we can see that that will be now 273, because that is 0 degrees. Okay, yeah, 273 Kelvin. Again, we have temperature 2 as 373 Kelvin. So when you subtract that, will give you just 100, okay, Kelvin. So I'll put 100 Kelvin there. So I'll just put 100 Kelvin. Okay, so we can see now that in fact, forget about the units, because I've even left some units for calories and the moles. So I know they go to say I need to have calories, because they will cancel at some point. All right, so what I need to do is I'll say 4 times that 5, that is 20. 20 times 100, so I'll say times 100. So that will give me 200. In fact, it need to be 2000 because here it's giving 20, so that is 2000 calories. Okay, so the units will be cancelled because, okay, I'll demonstrate on this one. So we know to say enthalpy will be given as the number of moles change. We know it's what, 4 moles, then times we have now for CP as 7.7 point, in just in short 7 point calories, all right, per mole, all right, then times the change in temperature. So change in temperature is now what, so here it was more degrees, so there was temperature there. Okay, then the change in temperature now is 100 Kelvin. So this Kelvin and Kelvin goes, and this moles and this moles goes. That's the reason why we remain just with calories. So you multiply 4 times 7 times 100. That will give us what? That will give us 2,800 calories when you punch on a calculator. So this is the work which was supposed to be done by change in enthalpy. So that is it. So that is it. Let's go to the next question. So calculate the amount of heat necessary to raise 213.5 grams of water from 25 degrees to 100 degrees. So molar heat capacity of water is 18 calories per mole, or just per mole per Kelvin. So what we need to know is that heat capacity, okay, is given as Q over temperature. All right, we know this. So meaning that there will be change in temperature. So say C is given as dt, not really this, I'm saying Q over dt, right? So meaning that Q, calculate the amount of heat necessary. So say Q will be given as C, okay, delta T, like that. So we can see that we have been given the heat capacity and the change in what, in temperature. So now the thing is, we need to result at joules only, all right, or just calories. So what I'll need to what I'll do is I'll have a go of cancelling these moles that I have there. Temperature will go with this. So if you can notice him, so the capacity is given as 18, all right, calories, okay, then over we have more there, which is per mole. Again we have Kelvin there. So now change in temperature will be given as so we have 25 degrees, which is plus 273, right, which will give us 298. Then this is our T1. Then T2 we have 100, so that will be just 3 that will be just 300, no, 373 Kelvin. Okay, this is our T2, this is our T1. So what I'm going to do here is dt, there is change in temperature. So I'll say 373 minus 298, right? Then from there, I'll cancel this mole by bringing the number of moles there. So we know we have been given 213 grams, right, of water. Then what is the molar mass of water? It's 18. So 18. So I'll go put 213 there over, okay, 18. Then this will result in 2 moles. So we can see this mole and this moles goes. This temperature from this temperature also goes. Okay, so just a matter of multiplying, and you have calories. So when you punch that on your calculator, you are going to get since, okay, so you are going to get 16. Okay, after punching that you get 16 12 calories, like that. Then I can take into kilocalories if I want, by dividing by 1000. That would be 0 1 2. So this point then will come there, then will be kilocalories. So this is what we are supposed to write. Okay, so from there we can go now to this question. It says 3 moles of an ideal gas, okay, given CV at 10 atm and 0 degrees are converted to 2 atm at 50 degrees. Find change in internal energy and also change in enthalpy for the change. So we have R as given like that. So what we need to do is I'll say, since I have V here, all right, so meaning that I will relate to change in internal energy as equal to change in number of moles, then CV, then delta temperature. All right, so from here then it's just a matter of substituting, so number of moles they are saying is the 3 moles of ideal gas, so we'll write 3 moles, then times the heat capacity. Now I mean the CV constant volume is now 5 calories, then P, which is degrees more. I don't know why they wrote this, it was supposed Kelvin more. All right, I don't know why they wrote this. So now what we need to do is, okay, we'll write 5 calories, then times change in, so there's supposed to be K and D more, okay, these calories. So now we have change in temperature, which we have from 0 to 50. So when you add, so have at 0 degrees it is now at initial temperature, which is T1, that would be 273 in Kelvin. Then at second, now 50 plus 273, that will give you what? 323. So I'll say 323 minus 273. So when you punch that on your calculator, so this is Kelvin. So this Kelvin and Kelvin will go, the more will go and the more. So we are going to have 1050. 1050 when you punch that on your calculator, calories. Okay, so that's how it was supposed to be approached. Now we have calculated this, we also need to calculate this change in enthalpy. So how do we calculate change in enthalpy? All right, so change in enthalpy will be given as the same number of moles Cp, all right, then change in temperature dt, or just change in temperature. So the number of moles is 3, that's what they said, then times the Cv. Now we know that Cp is equal to R, okay, plus Cv. You get? So the Cv that we have is 5, so I'll say Cp is equal to R is now 2, so I'll say 2 plus 5 for the Cv. Cv is that, so that will give me 7, right? So that will give me 7. So Cp, I will say it's 7, then times change in moles, I will say 323 minus 273. Okay, then that will, when you punch that on your calculator, it will give you that will give you what? In fact, here, all right, when punching here on the calculator, I've made a mistake. Here, when you punch on your calculator, it will give you something like, okay, I use the phone, so it will give you something like, since 5 times that will be just 75. Okay, 75, 750 in short calories. So that's the answer that you're supposed to get. Now here, multiplying this, because I've realized that it is giving the same answer, so I'll say it is 1050, all right, calories. Okay, so that's how you are supposed to calculate this question. Let's go to your next question. So we calculate work for adiabatic reversible expansion of 2 moles of an ideal gas at 273. So under adiabatic, there are things that are related we can have. So when you want to see change in temperature, you say T2 over T1, then which will be given as P2 over P1. All right, with the power, you say it's gamma, all right, minus 1 over gamma. Again, the same thing, this can be equal to V1 over V2. Then you just say, you just write 1 minus, no, the same gamma minus 1, just like that. Okay, so you master this. It will be used under adiabatic if you have been given the change in volume. So you find the final temperature as this, and by equating this to this, and also if pressure is given, you equate to this one. So now what we need to do is, and we need to know that Cp, okay, we have been given Cp. Have we been given here? Okay, calculate W for the adiabatic reversible expansion of a gas at, okay, we haven't been given some data here. So what I will do is calculate work for the adiabatic, and we need to know that work under adiabatic will be given as, so work under adiabatic will be given as nRT. Okay, then change in temperature, which is T2 minus T1. Okay, then over 1 minus gamma. So this is what we use. Now that we don't have T2, we need to find T2, right? So that we can use our formula well. So I said you bring this relationship. So I'll say T2, all right, over T1 is equal to P2. P2 is now to a final pressure of 2. So I'll say 2 over, the first pressure was 20. So I'll say 20. All right. Then to the power, all right, is gamma minus 1 over the same gamma. All right. So now, I don't know, I'm lacking data here. So I've left. For the question it was supposed to be given, let me just check on this question paper. Okay, I left some data. Okay, there was a data which was missing, which is Cp, and it was given as 5 over 2 R, and Cv was given as 3 over 2 R. Okay, so now how am I going to calculate this gamma? So gamma will be given as Cp over Cv. All right, so we have Cp as 5 over 2 R, okay, divided by the same Cv, which is 3 over 2. So you see that this and this will cancel if I reciprocate, so that will just result into 5 over 3. Okay, so that's my gamma. Is that clear? So now what I'll do is I'll substitute now, go, what is it that I'm lacking? So I'm here, so I have T2, then T1 I already have as 273, so 273, okay, then is equal to we have 2 over 20 by the way, then we have gamma, which is 5 over 3 minus 1 over again 5 over 3. Okay, so when you do the multiplication there, all right, so we'll say T2 over 273 is equal to 1, let's say, over 10 when I simplify there. All right, then I'll have what is there. I have common denominator 2, so that will be 4. That will be 3. Then times, now I'll reciprocate this one, which is now 3 over 5. Okay, 3 over 5. So from there, then I can say T2 will be given as 273, then open bracket 1 over 10 to the power, we have 3 over 2 there, times, alright, times the same 2 over 5, like that. So punching that will give us what? That will give us as T2 is equal to 10, alright, 108.8 Kelvin. So now it's just a matter of substituting. So we know work will be given as change in moles. We have 2 moles, right? Then the gas constant that I'll use here, I can choose. I'll use since there is no calories I can see, so I'll use even 8.314. Then times what is now, so the units will cancel, it will result in 2 joules. So change in temperature is now, we have 108, so meaning that it was being compressed. Okay, 108.8, alright, minus 273.2. So the temperature was being compressed, it was reduced, so meaning that we'll see how it will affect the value. So then over, by the way, I've forgotten the over here. So we have 1 minus what is the value of gamma? That is 5 over 3. So when you punch that direct on your calculator, you are going to have 4,100 joules. So this is the answer that you are supposed to have when you punch that on the calculator. Alright, so the next question that we'll do is at 25 degrees for the conversion of 1 mole of liquid benzene, the heat reaction at constant pressure is given by, okay, so this is just now the conversion of benzene, then giving us carbon dioxide and H2O. So what will be the heat of reaction at constant volume? So what we need to know is that enthalpy, okay, which will be relating the heat. So enthalpy will be given as change in internal energy plus PV, right? Now the PV that I'll use here, I'll say change in internal energy plus nRT, alright? So I can find work by using these changes. We have temperature there, we have also the value of that. So now I have enthalpy as well. So what will be the heat of reaction? So the heat of reaction is now the energy change. So I'll say making energy change the subject of the formula. That will be, this will go there. That will be change in enthalpy minus nRT. So the change in enthalpy now is negative 70980. Alright, minus the change in moles. What will be the change in moles? So we can see now is that this is supposed to be 7. Okay, 7 times that, so that will be, this is liquid, this is gas, this is gas, this is liquid. So we'll just say product, we have 6 moles. This one we don't consider it. So 6 minus, here we have as a reactant, we have 7.1 over 2, which is just 6 minus 7.5. So that will give me negative 1.5. That's the change in moles. So I'll say this is now negative 1.5. Okay, the gas that I'll use, the gas constant that I'll use okay, so if I have something related with calories, so I'll use 1.98, alright, 7. Then the temperature now is, what is the temperature? 25, which is 298. 298. Okay, so from there, when you punch that on your calculator, you are going to get negative 78, all right, 008.6 calories. So this is the answer that you're supposed to get. So that is it. You just need to master these guys. All right.